go.
Hey everybody, this is Dracula coming at you live from the Magic City. Yeehaw. Welcome to our stream. It is episode 3000. This is our 3000th live stream. Well, not exactly. It's like the 3000th day of live streaming. Sometimes we stream more than once in a day. So we're doing that and studying for Larry's science final exam. Final science. The final science. What were we on here? Can energy be created or destroyed? Oh, that's an easy one. Oh. Okay, so what he said. Why not? What happens to it?
It just gets...
Oh, hang on, let me turn on your... It just what?
It just goes to other atoms.
It's just transferred.
Yeah.
So, if there's a chemical reaction, which is endothermic, which is synthesis, or what's the opposite of combustion? It doesn't look like that's going to be on the test, but like electrolysis, you taking the water, the hydrogen and the oxygen and separating them, you have to use electricity to do it, so you're applying energy to the molecule, which is moving them into a higher oxidation state. The hydrogen and the oxygen, how many so the H2 and the hydrogen, they all have more energy stored than the water does, so when the combustion reaction happens, the heat is released. Okay, so yeah, we covered this already. Exothermic and endothermic reaction. Activation energy, what was that?
So that's the amount of energy needed to cause a chemical reaction.
So you got your fuel and your air mixture, and you compressed it, and then you got a spark plug.
Yeah.
That electricity is the activation energy that starts the combustion reaction. But then the rest of it is just the fuel and the air combusting.
So wait, does combusting make it easier, or not combusting? Does compressing make it easier for combustion?
Well, you're using the expansion to create the motion, so you want it compressed when it.
Yeah, but does compressing it make it easier?
But yeah, remember I told you that's how a diesel engine works. It compresses until the heat. When you compress it, the heat. It raises the heat until it reaches the critical point, and then that's why diesel engines don't need spark plugs, because they
heating coil things. Right?
Well, that's just to heat it up. That doesn't cause the ignition. The ignition's caused by the extreme pressure, and once it reaches at the full throw and it has compressed completely, it's reached a critical point, and it starts the combustion reaction. But that energy of the piston compressing is the activation energy in the diesel engine, and that creates so much heat that it starts the combustion reaction. Boom. So it doesn't have to be electricity. It can be just what do you call that when you compress gas and it makes a noise?
What's it called? So you could make a diesel engine that you don't need any electricity.
Right, just the starter to start it turning to start, the motion.
Or you could just do it like a Beetle. You get the belt on it and you pull the belt.
This is why we have the issue with runaway diesel engines. You know what that is? You know why turning off the ignition doesn't stop it? because it doesn't have spark plugs.
Yeah.
It just so you gotta. There's supposed to be a there's supposed to be a baffle that you close that cuts off the air to the diesel engine.
Oh, but then people just leave their turbos with nothing like that.
Turbo.
Yeah, though, because most diesels have the turbos, they don't put a freaking intake or anything on their turbo, so it's just the open thing.
Oh, no air filter, you mean?
Yeah, and what's it called? What am I gonna say? I saw someone, they had a semi-truck, and it was doing that.
Uh-huh.
And, what's it called? They had to put it in 5th gear and just release the clutch really fast. Or, not 5th, but like whatever's their highest gear. And just release the clutch really fast so it would stall the engine. And the truck lifted up like this.
Yeah, that's dangerous.
Really?
If you can open up and get to the air intake and shove
like a
you know,
paper or like
now you gotta take your shirt, you shove it into one side, and you take your pants and you shove it in the other. That's the only way to stop it. Yeah. And you're standing there naked, but you got a truck still. But
yeah, I saw someone, they got like a, well, either they got a cloth or they just stopped the turbo to slow it down, but it was a video there, the thing started speeding up and they got something and shoved it right on the turbo when it stopped.
yeah, that's the air intake. I guess they just had the turbo just like open. It wasn't.
Yeah. If you search runaway diesel, it's gonna be like the first thing to show up.
So, what was it we were talking about energy being created or destroyed? The law of conservation of energy, which states that energy cannot be created or destroyed.
Yeah. Just like the conservation of matter.
How do chemical equations model chemical reactions?
They show like what things are combining, basically, like
it shows the products and the reactant.
Yeah.
It shows the reactants and how many of it, which and what products you're going to get afterwards, and the quantities, and what? Oh, you're going to show me a runaway diesel?
Yeah.
Yeah. So where's
show something on the turbo?
Yeah,
cut off all the air. So
yeah.
It would stop.
So what'll happen sometimes is if you get a crack in the
and the oil starts leaking into the turbo.
No. Well, I guess a blown seal.
Or something like that, where
air is getting into the engine from somewhere it's not supposed to be coming from, and then you get a runaway diesel.
Oil usually.
Yeah. You could shut off the fuel. You know, there's supposed to be a fuel shut off on diesels also.
Yeah.
But so it doesn't just
blew up. Truck started shaking so much.
So include the arrow symbol, coefficients and products and reactants in your response. What the arrow? Okay, so the arrow goes where?
The arrow is like in between the reactants and the
products. Okay,
to
which way?
Which one turns into which one?
What? Well, not necessarily. Which way does the arrow go in a combustion reaction?
Towards the
Well, you're going to the. It's going to the right. So where are the products?
On the right.
On the right. All right. And so how would you rewrite that to make it the opposite, to make it the electrolysis that I was... You would put water on the left.
Yeah. And
that would be the reactant then.
Yeah, then it basically be decomposition.
Yeah. No, it's not a decomposition because you're adding... you're adding energy to it. When you make the hydrogen and the oxygen, you're building those molecules out of water. They are at a higher state than the water is. So that's a synthesis. That's an endothermic reaction. You're adding energy to the system, and yeah. Anyway, so what are the coefficients in 2H2O? Which one is the coefficient?
The two?
Which two?
The first two.
The first two.
The big two. Yeah. Big two on front of it.
The big two on there.
Two.
Things to know. Evidence of chemical changes. We already did that in that first part up there. Working chemical equations. Calculating molar mass. Calculating mole mass. Would you take the atomic mass and multiply it by what?
To 6.2 something.
6.022 times 10 to the 23.
Whatever the heck you said.
And then that will give you the mass of 1 mole. Or you can just look at a periodic table that has the molar mass. But usually the periodic table has the atomic mass. But you know the number of atoms it's going to be. If you need 1 mole. Mike Reagan, what's happening?
Nice. Oh.
What is this? Oh, it's Mutant Swarm at Serenity Academy. I'm gonna go to Port Stimson. Sabotage. Compare oxidation and reduction.
You said oxidation and reduction? Oh, reduction. Oh, now I know what you meant. Yeah, reduction is they gain electrons, and oxidation is they lose.
So, when you take water and you turn it into hydrogen and oxygen, which one is gaining electrons?
Wait, see?
You got H2O, all right?
Water, yeah.
And then you use electricity to the electrolysis reaction, which produces O2 and H2, right?
Okay.
All right. So
From water?
right.
Yeah.
So which ones are gaining electrons? How many electrons does hydrogen have?
Oh, the hydrogen would gain electrons.
Right, so hydrogen and then the other hydrogen, and so each hydrogen now has 2 electrons because they're sharing, it's a covalent bond. So, and now how does the O2 bond?
What, how does it become O2?
How many valence electrons does oxygen have?
6.
6? Okay, so how does it bond? Is it a double bond, a triple bond, single bond?
Oh, with hydrogen?
No, oxygen. Just
two
oxygen
oxygens?
atoms.
It would be
an oxygen molecule. How do the 2 oxygen?
Double bond.
Double bond? So, well, they each got 1 free electron after the bonding? What kind of bond is it, the double bond? Is it double covalent bond?
Covalent, yeah.
Okay. So if they got 6 valence electrons, how are they staggered? 2, 1 and 1, right?
Yeah.
Okay, so are they also gaining electrons?
Is what?
The oxygen atoms. if it's a covalent bond, they're each filling the outer shell.
What do you say?
All right, so you got 2 oxygen atoms, right?
Yeah.
Each of them's got 2 empty spaces on the on the outer shell, right?
Yeah.
So you got a double covalent bond.
So that those two.
So they each fill up their valence shells
Yeah.
by sharing those electrons.
Yeah.
So they're both also gaining electrons. What?
Someone was driving their car upside down.
No, the wheels. When a car spawns in, they're making it where the wheels are up higher so it doesn't get stuck in the ground.
Oh. Okay. Anyways. Yeah.
But once it instantiates completely, it looks normal. But sometimes it glitches and stays. But I know about that from Unity, and knowing when you want something to spawn in, you want it to spawn like a little bit above the ground so it doesn't get stuck in the ground.
Yeah. So it'll basically fall down.
Yeah, just a tiny bit, you know. But if you try to put it right on the ground, sometimes it'll get glitched into the ground when it instantiates, when it spawns. So what were we saying? So all right.
Oxygen double.
So
bond.
are the reactants at a higher oxidation state or lower oxidation state?
A lower.
Let's see. Electrolysis. H2O. But no, H2O. Oxidation reduction. Alright. So we're going to look it up here. In the electrolysis of water, oxidation and reduction reactants occur simultaneously, splitting water, H2O, into H2 and oxygen, O2 gases. Oxidation, the loss of electrons, happens at the anode, where the water molecules are converted to oxygen gas and hydrogen ions. Okay, so reduction, the gain of electrons, occurs at the cathode, where the water molecules are converted to hydrogen gas and hydroxide ions. Okay, so there's also hydroxide then. Let me see. It's got a little picture here that shows HOH, which is water, and can we see that bigger? Here's the. Oh, maybe I should show you guys. Let me bring up window. Yeah, you guys can all see this, what we're doing. So you start with water, and then you got a reduction reaction where the H2 is turning into 2H2. This is showing that that's reduction. And then this is oxidation. So on the when it's water, you got +1 on the hydrogen side and -2 on the oxygen side. And then oxygen becomes O2, which is 0, and that's why it's oxidation, because it's losing the negative charge, and the hydrogen was +1 and now it's 0, so it's gaining an electron. It's reduction. It's reducing the positive charge. So you see reduction and oxidation.
Yeah.
All right.
Wait, because
It's the charge.
So the oxygen will gain. I mean, no, will lose electrons, right? Yeah.
The oxygen is losing electrons. That's.
And okay, so yeah, so and then hydrogen is losing.
And that's because the hydrogen was filling the two spots.
And you need 2 hydrogen to...
Yeah, to make a water molecule. And then they bond to each other.
Two hydrogen to make a water molecule.
Yeah, 2 hydrogen to make a water molecule. It's H2O, 2 hydrogens and 1 oxygen.
Never mind. Okay, I'm stupid.
So, remember I told you that the water molecule is polar? You have an oxygen, and in the middle you got 2 hydrogens. The which one's more electronegative? The oxygen's a bigger molecule, so it's pulling the electrons towards it. So, what?
Molecule.
Okay, the atom. It's a bigger atom.
Yeah.
Than the hydrogen, so it's pulling the electrons towards it, which gives each of the hydrogens a +1 and the oxygen a -2 electrical charge. That's why they're polar and they stick together, and they're liquid at room temperature because they want to stick together. Like Siamese twins. Hey, you guys are stuck together. So anyway, when you use the electrolysis reaction to break them into hydrogen and oxygen molecules, you're adding energy. The hydrogen is losing, it's gaining back its electrons basically, and the oxygen is losing the electrons from the hydrogen, and so your charges ended up being neutral, and so the hydrogen and oxygen molecules are not polar. The oxygen is becoming less negative and the hydrogen is becoming less positive. Anyway, that's reduction and oxidation. Can you remember that?
Yeah,
okay.
Yeah.
So it's both happening at the same time. It's not like the reaction is sometimes yeah, well, anyway, this is the simplest electrolysis reaction I could think of. It's the opposite of combustion. All right. Let me turn this window off. Hi everybody. If you came into the middle, I'm playing Defiance and I'm helping Larry with his study for his final exam in science class. Yeehaw. What was the next one? So we did oxidation and reduction, and we did the energy changes, right? Reaction rates and equilibrium. You remember what equilibrium is?
Oh, that's something. It's about the chemical, formula thing, right? Well, how did I forget what that's called? The chemical reaction formula thingy.
Chemical equilibrium. Alright. In a chemical reaction, chemical equilibrium is a state in which both the reactants and the products are present in concentrations which have no further tendency to change with time. So the reaction's done. You got products and reactants, and then so there's no observable change in the properties of the system. So we'll look at this really quick. What is equilibrium in chemistry? We'll let you guys look. So here you got your reactants, which you have a high concentration of reactants and a low concentration of products, right? And as the reaction occurs, you're going to have less and less reactants. You're going to have more and more product. Oh, excuse me. All right, so what happens when you got, you know, hydrogen and oxygen in a combustion reaction and the containers start to fill up with water? You still got hydrogen and oxygen in there, but now it's full of water and you can't have combustion anymore, right? Equilibrium. The concentration of reactants drops down in the products, and so basically they, in order to have any more reaction, you would have to remove the products from the system so that the reactants can start reacting again. But because there's so much products in there, it's reached a point where there's no more reaction taking place. That's chemical equilibrium. Got it? What?
Wait, say it again?
Nope. You got a container full of hydrogen and oxygen, and you start a combustion reaction.
Yeah.
And it's like it's a closed system, a closed container, right?
Yeah.
So as that combustion reaction starts to take place, what are you gonna have in that container? Water, which is the product of the combustion reaction, right?
Yeah.
So now you got a container full of hydrogen, oxygen, and water. Can you keep having a combustion reaction when the thing's like half full of water?
No.
So why?
So it keeps changing back to hydrogen.
Yeah. So all right. Imagine. So the car, if you didn't have that exhaust stroke to push the exhaust out and bring in fresh fuel and air, it's not going to fire again because it's full of exhaust.
Is there a way we could just
Melina's
convert
smelter
that
is on the verge of
exhaust
melting.
back
To shut the place down, we need to hack the computer terminals
so
throughout
that
the
we could-
compound.
Well, yeah, we could feed it to a dinosaur and they could die, and then get buried under magma or
a quick way?
sink to the quick way.
Can you show my screen? I'm about to bomb the Pridwin.
You're about to bomb the Pridwin?
Yeah.
Okay. Matthew wants you guys to see him bomb the Pridwin. We got, make some noise over there so I can see.
Hi.
No, not on the microphone, in the game. Make some game noise. Is the sky purple on your screen?
No.
Why does it keep doing that? What is the map? Hang on 1 second. Don't do anything yet. Let me see. Map. Okay, filters. Color correction. Hue shift. Look at the sky. Look at the sky. Not that high up. Where there's color. Where you can see blue. See, alright, now don't move. Let me try to... Stop doing that. I need to see the sky.
Hey God, there's a vertibird in.
I want to... okay, now the sky's blue. Alright. Okay. Now, bomb the Pridwin.
Okay, hang on. I need to give them the order to fire.
Okay,
Hi, General. All the settlements are reporting in. We're ready to fire.
so that's equilibrium. Which has more energy stored, water or hydrogen? Can you light water on fire?
It's water. Oh wait,
No, the hydrogen.
no. So it lets it off when it becomes.
Yeah, oxygen
Oh,
and
yeah, 'cause-
hydrogen that have the energy stored.
So when water is made, that's combustion.
Yes, water is one of the products of combustion.
So
In your car, part of the exhaust is
All
water
right.
vapor. There's a certain amount of water vapor in the exhaust. but you got a bunch of carbon in there. That's why it's not like a hydrogen reaction. All the other fuels are hydrocarbons, not pure hydrogen. So energy changes.
Oh my god.
Hydrogen and oxygen have more energy. Water has less energy. Reaction rates. What do you think that is? Oh, look at that. There's a combustion reaction going on right there. What did you hit it with?
Artillery.
Wait, was that?
It uses hydrogen, right? The Pridwin?
Yes.
Sure.
It has like 5 trillion hydrogen.
Oh, hydrogen. Okay. I was like, are you sure it's combustion or is it the nuclear? Or
Is it nuclear?
Brotherhood vertebrates off in the
Matthew, was that a combustion
You said it
reaction
was
or
hydrogen.
a nuclear? Yeah, but was it a hydrogen bomb? Was it? Was it
Ooh,
nuclear?
it's an airship, not a bomb.
So yeah, it was hydrogen bladders. It was combustion.
said it? Yeah, okay. Combustion understream is not fired.
Oh, I don't know what that was. I
Looks
should,
like
you know
someone
what?
threw a Molotov or something.
Let me get in here. I'm safer in here next to this. All right, is that what you wanted us to see? You blew up the Pridwin?
Yeah.
All right, so Matthew blew up the Pridwin, and now back to our regularly scheduled program.
Now back to our not playing Defiance and studying.
All right, so that was the first page. Oh my God, how much stuff do you got to do?
It's a freaking finals thing. Of course I gotta do it.
Why is Newtonian mechanics? Wait, why use Newtonian mechanics if newer models are better? Newton? Because it's got fruit filling.
Because it's simpler and more accurate.
It's easy to understand, yeah. Newtonian physics.
We've got multiple targets. Let's take them out.
Rage consumes me.
Shoot.
Oh no, there's 2 of them. Alright, where was I? How do we study motion? Through a microscope.
Mechanics?
Yes, mechanics.
Or
What's my favorite? What's my favorite? Kinetics. What was the difference between kinematics? Kinetics. What's the difference? What when we looked up? What's the difference between mechanics and kinetics?
Oh, kinetics was part of mechanics.
Yeah. What was kinetics? It was objects in motion.
Oh yeah, it was the objects in motion.
And what was
I
mechanics?
think. And mechanics was motion.
Just
Like the whole thing.
let me
These-
look real quick here.
These. I think it was
These nuts.
I think it was these.
What is the difference between mechanics and kinetics? Look, we already asked Google. Mechanics is a broad field of physics that deals with motion and interaction of physical objects, while kinetics is specific, focuses on the relationship between motion and its causes, particularly forces and torques. So that's like causality? I don't know.
That's the end of that target.
What can tools help us? What can tools help us?
No, it's she did it weird. It's what tools can help us.
What tools can help us study motion? What do we use to measure?
Speedometers.
All right.
Tachometers? Is that what the RPM thing
Well, a
is?
tachometer, yeah, it measures how many times the motor turns.
Yeah.
The
So
speedometer,
that is motion.
yeah,
Speedometer.
speedometer, right? Velocity, right? Speed.
Oh
So what else do we have? We got the tachometer, we got the speedometer, we got an odometer. What does that measure?
Target destroyed.
Odometer. What does the odometer measure?
Let me build.
Distance traveled.
Oh, that's like the how many miles you got on your car?
Yeah. And how many miles it measures? How many miles your car has gone since it was built? So distance travel. Ah! What else can we use to measure distance?
Transmission from Aaron. I'll connect you.
I have a task I need completed. Your collaboration would benefit us both.
We need to gather some information. Nice work. Now no
Well,
one will be able to use
The
those.
distance, like very small distances, from like the end of the table to the middle of the table or something, or from one end of the table to the
We
other.
have to fend off the hostiles.
What would we use to measure that distance?
Like a ruler.
A ruler. There you go. For longer distances? Yeah, that's a tool. So for longer distances, a tape measure, GPS. So
I mean, it does tell you where you're going.
something simpler, not electronic. You know what? You ever seen two guys standing in the middle of the road? One guy's like way down there, and the other guy's looking through some kind of weird-looking telescope. Surveyors. It's like it's an angular measurement they're making. But there's also a rangefinder, which it's like a single monocular, like a small telescope that you just look through with one eye, and you can find the range, how far you are from the target that you want to shoot at. Anyway, I think we've looked at enough tools. How would you measure the angle, the direction you're heading?
Extraction complete.
Yeah.
Fantastic work. I will not have any second thoughts in bringing work to you.
And don't say GPS. I'll kick you in these nuts.
GPS. Direction.
Yeah. How do you get your heading? What tool do you use?
Compass.
What? That little pencil with the little thing on it that makes circles? No, I know what you... Yeah, it's a compass.
Bruh.
Konnichiwa. Oh, what? Kaguya. Konnichiwa. And it's here it's 11 o'clock at night, so it's konbanwa.
Oh, my magnet.
You dropped your magnet?
Yeah.
What else do we got here? So, all right, so hit are speed and velocity the same thing?
No.
All right, so what does velocity also tell you that speed doesn't?
Direction.
Yeah. You going north or south? Remember we talking about on the boat heading north, and then you throw your engine in reverse and start accelerating south? Are you traveling south, or no, you're slowing down?
You're going against the water, basically. So technically, towards the water, you're going backwards.
So if you are heading north at 30 knots, right? And you start accelerating east, what are you doing? Are you slowing down?
Wait, say
You're heading north at 30 knots, and you start accelerating to the east.
You're accelerating.
Are you accelerating?
Well...
Maybe you're accelerating, but in fact what you're doing is changing direction. Because the boat doesn't just
But
stop.
you're accelerating in this way, though.
Huh?
You're accelerating more.
You're heading north. It's going. Your speed is 30 knots. Your velocity is 30 knots north, and you start accelerating to the east. You're not going to stop heading north and then start going east. You're going to do this, and then you're going to be changing You're changing direction. That's why velocity is important, because oh, look at this. Danger at Diablo. What is momentum? And you can state Newton's law.
GPS. Momentum.
If you got a very large object that's standing still.
The rate at which something's moving.
No. Does it require more or less energy to make it move than something that is not as massive?
Yeehaw!
Alright, so you got an object, a massive object that's moving. And you got a less massive object that's moving at the same speed. They're both moving at the same speed and in the same direction. The more massive object has more momentum because of its mass. Dang it. Get up there. Dang it! Ah!
Shields are down.
That thing was massive. It had more momentum. These nuts!
Target neutralized.
What else is massive? No.
Oh no! Oh my god! Oh my god!
Oh, no taper fade.
Oh my lord!
No taper.
So, you understand momentum? If it's directly related to mass, and motion. Or, I'm sorry, velocity. Ah! Get... You know what low taper fade is? Yeah, but you know what it is. You know what it looks like? You know what a fade is?
Yeah. It's literally what it sounds like.
It gradually gets shorter.
Yeah.
It fades. So what's this taper? What's this taper? What's the taper? Taper fade. Does it taper in a short distance or a longer distance or? I think it probably a long gradual fade.
Or you raise your bloody hand if you like men.
What?
Huh?
What the hell was that? What the bloody hell was that?
I cannot hear.
Or you raise your bloody hand if you like men.
What?
What?
Or you raise your bloody hand.
Daddy,
What, Matthew?
is there anything we can do about my ear? Because
Hellbugs are colonizing
ears.
the
Or you raise your bloody
You need to
hand.
destroy those pheromone secretors so they'll never stop
Oh,
coming.
that's because of you're congested. That's because you're congested.
it's good just.
You can maybe take some
brat.
some ibuprofen for that. Non-steroidal anti-inflammatory.
I cannot hear.
Genius.
I cannot hear anything that my game is saying.
That your bloody ear.
It looks like the Hellbugs are set up in a cavern beneath the site. We can force them out by flooding these vents with poison. There should be some nearby.
What is? What did she say? And that's why I had it so loud, because I can't hear anything.
Is momentum conserved?
Only when there's like no other forces acting upon it.
You're right, in a closed system.
Yeah.
Remember, a closed system. In a closed system, momentum is conserved in a closed system. In space, nobody can hear your ice cream.
Seriously. Not my ice cream.
Is momentum conserved in space?
Yes.
Is it? Is space a closed system?
Yes.
There's no gas, so there's no wind resistance. There's no drag.
Can I please turn this up?
Yeah, you can turn it up a little bit. You turn up where you can hear it. Don't turn it up where it is distracting
Well,
to everybody else in the room. To where we're gonna get, radiation poisoning.
Moore's still down there. Give them another dose of poison.
What was I saying?
In space.
Low taper
Is
fade.
it closed?
All right, so you're not gonna get any wind resistance, or drag from wheels on pavement. But what is there in space? In the solar system, is there any drag?
More attackers incoming.
Yes, there is.
How? In space?
Yes. Within the,
in the void?
yes, in the void.
How's there drag?
There is solar wind. The sunlight coming, it's an angular force. It pushes on things. I'm just trying to express to you that the closed system is fictitious. It doesn't exist. Let's say there wasn't any solar wind. There's still gravity from the sun and Jupiter and Saturn pulling on things. If you got something in orbit, even if it's outside, that's passing the gas. If it's past the gas, there's still going to be drag, and its orbit will eventually decay, and it will. What do they say? Like 2066, the Tesla Roadster will plummet back into Earth's atmosphere and burn up on re-entry. Why? If space is a closed system.
I'm detecting a large amount of seismic activity. Be ready for anything.
Because it's not a closed system, there's still drag. But in a closed system, yes, momentum is conserved. It just doesn't exist. That's it. Give it a couple 100,000 years, it'll slow down. Whatever it is. At least that's our understanding of Newtonian physics. Dang it. Space is not empty, it's full of energy. Even outside the solar system, there's cosmic radiation, and the sun's corona is pushing out on us, and it protects us from that cosmic radiation. Yes.
Oh my god.
The corona is the sphere of the sun's influence. It's not exactly a sphere, but it starts from the sun and it pushes out, but it sort of elongates because the sun is traveling in a direction, and so it compresses on one side. That's the direction that the sun is traveling, the direction that our whole solar system is traveling. So it compresses on that side and elongates on the other. Just like a wake, or like
Mop up the rest.
Hey!
Oh my god!
What was that? Oh, they.
Would it actually, the Earth would, like, its magnetic field would eventually change?
That's what we keep hearing. There's evidence that it has flipped several times north to south.
Yeah.
By looking at iron filings in the who is this? Pyros?
What was that?
That was I cheered.
Why?
And because we won. Someone chanted evening.
That's what that is.
What?
Huh?
Let's see. So, is momentum conserved?
What?
Is momentum conserved?
No. Oh, yeah, it could be, I guess. In a closed
system. Speed, velocity, momentum.
Huh? What about it?
Speed, velocity, and momentum. What is the difference?
Speed.
Speed is how fast. Velocity is how fast and in what direction. And momentum is in relation to the mass and the velocity that it continues going in that direction. What do you have to do to make it stop going in that direction in a closed system?
Make it a not closed system.
You have to act on it.
Yeah, make some kind of force.
You have to exert force in the opposite direction to make it come to a complete stop, possibly, or to change direction sideways to make it go faster, accelerate in the same direction. How do we describe motion if velocity changes?
Speeding up or slowing down.
Which is
Or
also
changing direction.
which is also called
Acceleration.
acceleration or
Deceleration.
deceleration, or we'll just like if we're accelerating in the opposite direction, we call it deceleration, but we can also call it acceleration.
No, it's technically acceleration, just in a different.
In a different direction.
Yeah.
How does circular motion differ from linear motion?
The linear is straight and circular is circle.
It's a circle. It's a circle. It's a circle.
All these caps.
Centripetal. What is that? If you're going in a circular
path.
what happens
Ready to roll.
to the kids on the Gravitron? They want to keep going in a straight line,
Oh, but something
but it's
is pulling it.
right.
Yeah.
Gravity continually pulls us towards the planet as we are trying to accelerate away from it, and we end up, if we play our cards right, in orbit.
Oh.
Not flying off into space or crashing down into and burning up in the atmosphere, but we end up in a orbit around the planet, and that our momentum is being turned into circular motion by gravity. Projectile motion and trajectory. What is the path that a projectile follows? What is that called?
Distance? Wait.
No, it goes like a McDonald's arch or St. Louis.
Oh, parabola.
Parabola.
Something.
You say something is parabolic, but it's a parabola. You put the wrong emphasis on the wrong syllable. So projectile motion and trajectory are the projectile follows a trajectory which is in the shape of a parabola, a parabolic path. Imagine riding an amusement park ride in circular motion and constant speed. In that situation, you are accelerating. Explain.
Oh, because you're continuously changing direction.
Yeah, that force is causing you. So, all right. So think of it as you're traveling in a straight line, only you're constantly accelerating to the left.
Well, it's not a straight line.
What?
That's not a straight line.
Yeah, right. It's a circle.
Yeah.
But you're constantly accelerating to the left. History of mechanics. Well, I tell you, I was a mechanic back in the day when diesels would run away and you had to stuff your pants. You had to take off your pants and shove it into the air intake to make it stop.
What?
You were supposed to have a fuel shut off, but sometimes you had so much fuel line on the other side of that, it just run away with your pants. Frames of reference.
What?
So enough with the what every time. Calculating speed. Dude. Do you know why the unit for acceleration is squared?
Because it keeps changing.
How often?
Like every square second.
Every square second. So if you're accelerating at 9.8 meters per second square, every second you fall, you're going another 9.8 meters per second faster than you were the second before. So instead of calling it meters per second squared, you could call it, stop that! You could call it meters per second per second.
What is that? What sense does that mean?
That's literally what meters per second square means.
Isn't meters per second per second?
Meters per second per second.
Oh, it's how many meters per second you gain in a second.
Right.
Oh!
You got it? Meters per second per second. That's why it's meters per second squared. And we're gonna celebrate with a square cigarette.
Farted.
Alright, things you need to know. Speed versus velocity, calculating speed. You calculate speed how? Meters per second. You say, alright, in 20 seconds, we traveled 80 meters. How many meters per second are we going? You take 80, divide by 20, and we get 4 meters per second. That's how fast we're going. So in 20 seconds, we will have gone 80 meters. That's how you, hey, that's how you calculate speed.
I'll tell you.
Now, we're going to take that speed and we're going to convert it to American standards so we know how freaking fast we're going in miles per hour.
Yeah.
Because I have no idea how many meters per second I'm going. Kilometers per hour. In the United States, we can look at our speedometer on our cars and it says miles per hour, but there's little tiny numbers on like an inner circle on that speedometer and it says kph. So we can sell our cars in Brazil, since the numbers are the same. I think they use the metric in Brazil. Alright, so have we gone through all of this then?
Yeah.
Alright.
I guess if that was all of 11.
Alright, that's enough studying. Let's.
Yeah.
You're not gonna play Defiance with me, are you?
No.
Oh no.
Oh no.
No.
Oh no.
I don't think I am. Oh my no.
We're taking all the raiders, and we need to clear this place out.
I don't think I will.
Will get us one step closer.
Alright, bitches.
I'm not a.
Baloney, Zamboni, pony.
The turrets are down.
Down with the Tourette's.
Bruh.
We always did these, VR and I used to play all the time on PlayStation 3. And we'd be deactivating these turrets. And VR, I don't know if you guys know this, but he has Tourette syndrome. So it was a big freaking joke. We're deactivating the Tourettes. And VR stopped glitching. Nippon Gaki! If any of you know what that was that I just did, there's one person that I remember that actually got that. They knew what I was talking about because they had seen the same episode of this obscure television show that I was watching when the guy that had the Tourette syndrome did that. It's a Japanese guitar company, Nippon Gaki. Nippon, I don't know if I'm saying it right. Nippon Gaki. They make guitar. It was an electric guitar. They were trading it up. They were trading it for something else, or they were going to trade for this guitar, and they's like, man, I'm afraid the guy's gonna think we're not serious, and he's gonna not trade us the guitar because they had something that the guy wanted, and he didn't want the guitar anymore. He heard they had this, I don't know, a laptop or something. And they asked him if he'd trade, you know, if he had anything he'd trade for it, and he told him that he'd had a Nippon Gaki guitar. And when the guy heard this, his Tourette started acting up. And when he hears, you know, when he hears a word that makes his Tourette act up like that, he starts having like a reaction where he wants to keep saying the word, and he was like screaming Nippon Gaki. And they're like, I hope he gets this out of his system before we get there, because we might not get this guitar if he keeps doing that. But that was hilarious. That was yeah. I wish like everybody had seen that show so that everybody could just go Nippon Gaki. Got Larry over here doing Beavis and Butthead. Why am I at threat level 2? Where's the motherfucker? I got a stowaway out here somewhere. Chicken George. You talking about Chicken George?
Chicken jockey.
Oh, Chicken Jockey.
Chicken jockey.
People are rarely on the same page with me, which is why it was so great that somebody knew what I was talking about when I said Nippon Gaki.
Chicken jockey.
Chicken Jockey. Maybe I'm just strong enough now to make it threat level 2 over here, because I don't see anybody hanging out. Huh?
That sentry gun won't be giving us any more trouble.
Hello? Whoever's out there, we need some help inside the garage.
Let me the F out.
Thank God! We've been hiding in here for days without food or water. We're ready to take back our mine. We'll need to override the back gate to get to their leader. Follow me. And I'll open up the gate. Let's get those bastards. I need some backup.
You go rally the miners. All right, miners, let's rally.
I don't have a good feeling about this. They disabled the turrets. You're gonna have to take them out. What a mess. I don't know where the miners go from here, but at least the mine is safe for now.
Let's see what else we got. Defiant View, Mark of the Defiant, and Tar Family, the Daily Record. Alright, oh, and record sales I already did. So, the Daily Record, and so let's go look for the Mark of the Defiant. We'll start at Shondu's. If either of those were here, they would be, I think, right, no. The Mark of the Defiant would be here, and it's not, and the Tar Tracks crate would be right outside the gate, and it's not. So let's go to the next one. Happy pal to you until we meet again. It would be like here or here, somewhere along here. And I think the crate would be over there, but it's not. So let's go to Iron Demon Ranch. Alright, so the mark would be, I think, along this fence or over here, but it's not. I would see it on the mini map, and the crate would be over here next to these rocks. Bloodbath Turnout. This one you can't see from the fast travel. You gotta go this direction. So it would be on the wall, and I think there might be a crate over that way. Anyway, or it may be up there, but I would see it on the mini map if it was there, and it's not. So Earth Republic camp. Yes. Look, there's a Tar Tracks crate. And I think, like, the mark would be here? I don't quite remember. But I know where the Tar Tracks crate is, and it's on the mini map, so let's go get it. And this usually ends up being some arc salvage. Alright, let's keep going, looking for that Mark of the Defiant. Let's go to Last Chance. It would be right there, and it's not. Headlands Transit Depot. No mark. Be on this building somewhere. Diablo. I think over there somewhere. Bug and Chug. I'm actually not sure where the mark would be. Like, on this bus? At Bug and Chug? Did I miss any place? Top Notch Tool Works. It's not here. Moyer processing. I think the mark would be on this, and the crate would be like over there somewhere. The crater. The crate would be under this bridge, and the mark, I don't remember really. I think the mark of the Defiant was on one of these buildings. Alright, Shonda's consulate, I was there already. Let's check Coit Tower. We're looking for the mark of the Defiant. I think the mark would be on the statue. And the crate would be like over here somewhere, I don't know. Overpass. So there's a building right over here.
I'd like to trade some items.
Where the crate would be, I guess the mark would be there also. Fork. God dang, ain't no mark of the Defiant nowhere. Port Bruno. Water Temple.
Just looking to trade a little.
Yeehaw!
Oh, look at that. Ego evolution. Swim a total of 10,000 meters. Or 1,000 meters. think sometimes the marks out there.
An incoming arc fall. I have high hopes for this, but let's be careful.
Yeehaw!
Yeah, no. Anyway.
I'm busy.
We've got multiple targets. Let's take them out. Multiple targets. Let's take them out.
Alright, I'm gonna make the rounds again. Well, there's one place I forgot to check. Tranquility. Of course, somebody may have gotten it I was, you know, not. There it is. Cut check. Let's try Earth Republic. Gotta keep jumping around until I find the mark of the Defiant. I think it's here.
Time to go.
What did I remember used to be up in here? Oh, look at that. Yep. Here it is. Trying to flank me. Changed his mind. Wow, look at all them side missions. Look at all those side missions. Or side quests. Let's see if there's anything else I can do. Soleptor. Complete a Raider Expo. Commandeer Cronkite. It's almost 12 o'clock though. I've been going about an hour and a half. But I was up late last night. I need to get some sleep tonight. But this was episode 3000. We have done 3,000 days worth of live streams since I started live streaming. Oh man, how long ago was it? Well, what's 3,000? That'll give me a rough idea. Let me bring up a calculator app. There you go. 3,000 divided by 365 days. 8 years ago. I started live streaming 8 years ago. Missed a few days here and there. But I remember for the first 1,000 episodes, I was streaming every day. For about the first 2,000 episodes also. We had a hurricane. Power went out. Streamed a little from my phone. Went on a trip here and there. Did some live streams from my phone whenever I could. So, we missed a few days. But I named the next episode. It's not like I skipped any episodes in so it's been more than 8 years. You know, by who knows how many days. But yeah, 3,000 episodes, and I'm glad you guys could come out and see it. And Defiance is back, man. We've come full circle. This is what I started streaming 8 years ago, Defiance. And for my 3,000th episode, streaming Defiance. That's all, folks. Y'all come back now, you hear? Thanks everybody for coming out to watch the show. It's been a lot of fun. If you guys want to help support the channel, smash the like button, subscribe, and share. Come back tomorrow for episode 3001. The Space Odyssey continued, or something. Anyway, I'll see you guys then. Till then, happy hunting and yeehaw!